Very, very good morning to everyone who is listening. So for those of you who don't know me, my name is Chris Stewart and I coordinate training activities at the European Centre for Medium Range Weather Forecasts. Today, this is the third day of the joint ESA, EUMETSAT and ECMWF training on atmospheric composition. And today we have a very interesting program of presentations on data assimilation and satellite applications. So the first part will be on data assimilation applications. And I have great pleasure in introducing Inness and Jérôme Barre, both from ECMWF, and they will present data assimilation for atmospheric composition, applications and challenges. So I would invite, I think Inness is going to begin the presentation. So I would invite her to begin the presentation.
Right. Can you see my screen?
Yes.
Yes.
Yeah.
Okay, then I'll start. Yeah. Good morning, everybody. I'm Inness from ECMWF, and together with my colleague Jérôme Barre, I will tell you a bit about data assimilation. So you heard already a lot in the course about satellite instruments, satellite applications and models. And we now tell you how to combine these using data assimilation to produce operational atmospheric composition forecasts. So I will start off with giving a very short overview of what the Copernicus Atmospheric Monitoring Service is about, and then start some basics about data assimilation methodology and highlight some issues that we face when assimilating satellite data. I then finish off with introducing the concept of reanalysis and pass over to Jérôme for the second part of the talk. So we both work for the Copernicus Atmosphere Monitoring Service, CAMS. This is operated by ECMWF on behalf of the European Commission, and we provide operational services for atmospheric composition similar to NWP and weather forecasting. So we combine, I just change the pointer. So we combine Earth observations with state-of-the-art numerical models to produce 5-day forecasts of atmospheric composition. At the heart of it all is our global model, which has a resolution of about 40 kilometers and which runs every day or even twice every day to produce 5-day forecasts. These global forecasts are then used to drive an ensemble of regional air quality models over Europe that produce higher resolved air quality information. And then the output from both the global and the regional system can be used by downstream service providers to provide a range of products for users. For example, there's a SunSmart app that gives UV alerts. The Windy app displays a lot of our products. We have air quality bulletins on Euronews and also CNN, and national environmental agencies can also use or benefit from the data we provide. So how do we do this? Right, to get a good forecast of atmospheric composition, we need a good initial state of the atmosphere. So we have our forecast model and we combine it with satellite data in what we call optimal way to produce the best possible initial conditions for a numerical forecast. And this optimal is meant in a statistical sense. So we minimize the error of the analysis, or we maximize the probability of the analysis being correct. And CAMS uses ECMWF's 4-dimensional variational data assimilation system, or 4DVAR in short, to do this. And this schematic here illustrates what we do. So we look at what we call an assimilation window, in our case here 12 hours, and we have a forecast here given in blue that shows us one representation of the atmospheric state during this window. This forecast often comes from a previous model analysis. We call this beginning here the background. We also have a different representation that is given by observations for the same window. And you can see these two don't agree. So what we do is we optimize our initial conditions. So we change the beginning of the forecast to produce a forecast throughout the window and beyond that fits these observations best. And we talk about 4D VAR because it's the three-dimensional space and also the time dimension taken into account. So we look at the observations actually at the observation times. Currently, we minimize the initial conditions. For atmospheric composition, it might be better to optimize other parameters, for example, emissions, and Jerome will talk a bit more about that. So what we do looks like this in a mathematical way. We have what's called a cost function. So that is a global measure of the misfit between the current state, which is this X, and a background, which is our beginning at the window, and the observations and the current state. And what we are doing, we are looking for the X that minimizes these cost functions. So the individual terms here are X, our control vector. So that's all the variables that are adjusted as we are looking for the analysis. This is our background, our model state we start from. This often, as already said, comes from a short range forecast. These are the background error covariance matrix, and we assume all the errors are unbiased and Gaussian. And then we have a similar term for all the observations. So here the Y's are all the observations, and we calculate the model equivalent of the observation and compare those two. And here we need to specify the observation error characteristics. So in this formulation, we assume our model is perfect over the assimilation window. And that's called a strong constraint 4D VAR. If that isn't the case, we could also add a model term as a third term to this equation and minimize it with the other terms. And Jerome will tell you more about the methodology, how we actually go about finding the analyses in the second part of the talk. So if we look at a control vector, so these are all the variables that are adjusted as we are looking for the analysis. We have a range of meteorological fields, the typical fields that are in ECMWF's integrated forecast system. So we have vorticity, divergence, temperature, surface pressure, and specific humidity. And then we added a range of atmospheric composition variables with ozone, carbon monoxide, nitrogen dioxide, formaldehyde, sulfur dioxide, and also some greenhouse gases, CO2, methane, and aerosols. For all these, we need models to describe the time evolution. And we have the ECMWF's IFS that contains all the NWP fields, but we've also integrated a chemical module for the reactive gases. We've got a greenhouse gas module, and we have an aerosol scheme. This is all fully integrated in the IFS, and these variables are minimized together with the NWP fields. So this is the basic concept. And as I already said, Jerome will dig deeper into this later on. And I'll now look at some of the issues that we face when we assimilate satellite data. So this is an example of the coverage for some species that we get during one 12-hour analysis cycle. So we look at CO data, ozone data, NO2 data, and SO2 data. So on the first glance, this doesn't look too bad. We have data from several instruments for all these species. But if we look in more detail, there's some obvious problems that we face. First, a lot of our data come from UV-vis instruments. So we only get observations during daylight conditions. That means half of the globe is not observed at any one time. So these information won't give us any information. These observations won't give us any information about a diurnal cycle or a diurnal maximum. Also, the data we use, a lot of them are total or tropospheric columns. So we have to work out how to put that information into the vertical model domain. We then use data from low Earth orbit satellites, and yeah, these have fixed overpass times. Often, yeah, we have thin orbits, and it'll take a few days before we build up global coverage. And then even data that come from the near infrared or from the microwave that can give us information during the night might be affected by clouds because, yeah, the retrievals don't work in cloudy conditions. So we are still limited by that. So we have data like this that we put into our assimilation system. One thing we have to consider when we do this are biases that we might find between the data and the model. So our 4D VAR assumes that the errors are unbiased and is only designed to correct for random errors. But in reality, if we look at the global mean of the difference between the observations and the model equivalent, that is not always the case. We often have a value that isn't zero for the global mean of this. So we have biases. And we have our two terms here, the background constraint and the observation constraint. So the biases between the observation and the model can come from biases in the observations, for example, measurement errors, instrument noise, representativity errors if we assimilate in situ observations, but we have a 40 by 40 kilometer grid box. How do we map that? There can be errors in the model background, and there can also be errors in the observation operator when we map the model to the observation, for example, interpolation errors or model errors in radiative transfer models. Unfortunately, there's often no true reference to the real world. So we don't know what is true. We just know these two are biased against each other. So we need a bias model that can correct for these biases before we use the data. If we had only one instrument and one data set, we could spend a lot of time looking at that and working out a bias model that we could apply to the data before we assimilate them. For example, say there's a scan bias and we correct for this. But in reality, our system is very complex and the observations change a lot. And this is illustrated here. I think Vincent Henry already showed this slide yesterday. And you can see how the number of instruments increases with time, or has increased with time since the 1990s. And we now have over 70 instruments. So we need something that works automatically and does not depend on too much manual intervention. And for this, we use a variational bias correction scheme. So our original problem, again, was the background constraint and the observation constraint. And we now, for each of our instruments or our data sets, we come up with a set of bias predictors that might describe biases in the data. For example, they might depend on solar elevation, surface emissivity, thickness of the atmosphere. And then we add an additional term into our minimization problem where we have a background constraint now for the bias parameters. And we minimize this together with the other terms. We then have, instead of the normal observation constraint, now have a bias corrected observation constraint where we put this term in and remove the bias in the minimization. And this works very well. We now have a system that can spin up if we get new data. It can adjust to changes in model or data, and it removes biases. And this is an example from NWP where we look at an MSU channel that is sensitive or measures temperature in a sense in the radiances, and it is affected here. You can see these kinks by some cosmic storms, and the bias correction then changes completely after this. But the bias corrected departures stay quite similar. And if we look at temperature information from radiosondes, we can hardly see what has happened because this is quite stable throughout the period. So it's very important to have a correction scheme that can adjust to sudden changes. The next point I want to describe are the observation operators. So we need to map our model from the beginning of the assimilation window to the observation time and location. Well, we have our model forecast for that, but then we also need some integration or interpolation to match the observation quantities. And there's two options that we have. We can either directly assimilate the radiance observations. This can be very complex and requires a good radiative transfer model. For example, we have the RT-TOF in the IFS because we have to compute the radiances from the model state variables. CAMS is using this for the NWP fields, but it's not using it for the atmospheric composition fields at the moment. But we're hoping to explore this for ozone and also for the aerosols. The other way is to simply take the retrievals and assimilate those. If we do that, it is important that from the data providers, we get information about how these retrievals are characterized. So we need information about averaging kernels, a priori, error estimates, and also hopefully quality flags so that we can discard data that are clearly bad. So if we assimilate retrievals, I just have one example of a column retrieval. So think of this as a total column carbon monoxide field, for example. So the retrieval here is a linear combination of some a priori field, or vector or field, and the observed quantity, the truth, smoothed by the averaging kernel matrix A. And if we had a perfect retrieval, this averaging kernel matrix would be the identity matrix, and we would retrieve the truth state of the atmosphere. That is not always the case. So when we use these observations, these retrievals in our data assimilation system, we could do it in a simple way and just say we plug this observation in. It's a total column observation. We integrate our model field, calculate a total column, and then use that in our cost function. But this means we now have all the information that went into the retrieval in the differences between our observation and the model. And if you think you have a case where your satellite doesn't have any sensitivity to what it's supposed to measure, so you had here a zero matrix, we would be left with the a priori. So we would assimilate the a priori instead of any true information. We can do better than that if we design an observation operator, a modified observation operator, that basically uses the same structure that is used in the retrieval. So now we calculate the observation equivalent of the model using the averaging kernel matrix and the a priori. And if we then simplify this, we are left with this term. So now in the case of no sensitivity, this would go to 0. So our observation would not have any impact in the analysis. So it is important, even when using observations, to think about how you want to use those. And we still, even though in the end all those terms fall out, we still need the information about the a priori because we use it in the observation operator. So I've already mentioned total column observations and the difficulties that we might face to map these observations back into, or any increments from these observations back into model space. And this is illustrated here. So here we have a single ozone, total column ozone observation located here. And the increment we get from this observation looks like this. So you can see it's really spread out, thousands of kilometers. And this comes because the horizontal correlation from the background error matrix are crucial for spreading out this information. So we have to find a measure that works well and doesn't spread it out too much, but also doesn't confine it too closely to just the observation. We have the same issue when we look at the vertical distribution, because again, the model or the observation doesn't tell us anything about this. And for this case, we get an increment that peaks up here, which is around 25 kilometers up in the stratosphere, where, yeah, the ozone concentrations are largest. And this comes because our background error standard deviation is largest there. So the analysis knows the model has the largest error in this region and places the largest correction from any total column observation there. In practice, this can look like this. So here I look at an example of the ozone hole. This is going back to 2003, so quite some time. The top panel here shows a cross-section from the equator over the South Pole and back to the equator from our control, which is a model run without data assimilation. And you can see at that time, our model was not very good representing the ozone hole. We have here the high values of the ozone layer, and there's no ozone hole over the Antarctic. We then assimilated MIPA's profile data and get a very nice ozone hole in the analysis. Obviously, neglecting that we shouldn't have a bias model in the first place. We can then compare with ozone sondes. That's here the black line, and see the analysis captures this very well, whereas the original control, really doesn't have the ozone hole. So a year later, we didn't have any MIPA's data available, and we only assimilated total column observation. And now our analysis doesn't look so good anymore. So here the sonde is in red. And again, you can see the very low values here in the ozone hole. But now what we get in the analysis looks like this black curve, because our standard deviation the background error standard deviation is largest here. The largest correction is applied here in the wrong position. So it is really important to have as good a model as possible. And also, if we can use height resolved data, we know we get a much better analysis. Additional difficulties comes when we assimilate aerosol optical depth observations. So here we not only have the problem that we are looking at a column observation, but we also have a model, an aerosol model that has several bins, and by now it has 14 bins. So not only do we have to distribute the observation in the vertical and the horizontal, but we also have to split it into various bins. And the way we do it is that we add up all these bins to create a total aerosol mixing ratio, and remember the individual relative contributions of these bins. Then we assimilate the data, and then we partition the increment back into the bins depending on their relative contribution. Well, that is not always correct because they might have different lifetimes and over the assimilation window, or experience different processes, for example, deposition, sedimentation, differently. So this is not the perfect way to do this, but in the absence of better information, this is the only way we can do. And then it depends a lot what model variables we have, how these aerosol optical depth increments are distributed. This is a case going back to 2010 to the Eyjafjallajökull volcanic eruption that put a lot of ash into the atmosphere. But our model at the time did not contain any volcanic ash or volcanic sulfate parameters. So any signal from the AOD was placed here in a plume of sea salt, dust, and organic matter. We then improved the model and included feeds for volcanic ash and sulfates. And now an AOD assimilation leads to increments in these other species, and we get a better representation with fields in the volcanic or with contributions in the volcanic parameters. So to finish off, I just want to say a few short words about the concept of reanalysis. So we run our global CAMS system every day to produce daily forecasts. This system evolves with time. We usually work on improving the model and have 2 upgrades per year where the model changes. Also, the horizontal or the vertical resolution of the model can change. The observation usage can change, and the emission data sets might change. And especially during the last year, we changed the emissions a lot. That means what we calculate now is not necessarily comparable with what we did 5 years ago or even last year. And if we want to look at trends or at anomalies, we need a data set that is produced with a consistent version of the model. And this is what a reanalysis does. So we have a version of the model that is valid today, but we go back in time, and we go back to 2003 at the moment, and then run the whole period with that model version to produce a consistent data set. We also use consistent emissions and consistent reprocessed observations. And you can see the benefit here. So this is an ozone score at the Antarctic Neumayer station. The top is good, the bottom is not so good, and in black is our near real-time system. And you can see how it evolves with time. It's not very good at the beginning and then really improves. And how every year during the ozone hole here, it did really badly. If we run the same period with our reanalysis with a later model version, we have much better consistency. We still suffer here where we don't have any profile data for a few months, but on the whole, we create a much, much better data set. And data sets like that can then be used to look at anomalies. So this is an example from the Australian fires in January 2020. And we're looking at anomalies of CO and AOD against the mean over the years 2003 and 2019. So these fires put a lot of pollution into the atmosphere, and that was then subsequently transported over the Pacific. And we can really see this signal here in the elevated CO values. We can also see it in the AOD anomaly. And for aerosols, there were also observations that showed the whole, or not all of it, but some of the aerosols really made it all the way across the globe and came back to Australia. And then, finally, we can also use a data set like this to study trends. This is from a contribution we did to the BAMS State of Climate, where we looked at CO burdens. And you can see how over the globe this has changed and has come down during the recent years. You can see a very big spike here from big fires in Indonesia, which is also shown here in an area average over the maritime Southeast Asia continent. And you can also see that there were fires last year here in red. And we can then compare data with, this is TCON at Park Falls, just to get some feeling of the quality of the data. So if we want to look at anomalies and trends, we really need a consistent data set. And that's where reanalyses come in very handy. And I think that's me done. And I now pass over to Jerome to do the second half.
Okay, thank you, Antje. So now Jerome Barre is going to present the second half of this, this presentation on data assimilation. We have a couple of questions put to Slido. I don't know, maybe while Jerome is uploading his presentation, is sharing his presentation, I can ask these to you. So there's a question on how do you use the A kernel to characterize the satellite observations?
Yeah.
So maybe you could just answer that in a minute.
Well, we use them in the observation operator, like in the equation I showed. So we have the information from the data providers. We process them so that the observation that we present to the model have that information. And then, we apply the relevant equations in the observation operator, taking account of the averaging kernels and the a prioris to smooth the model data accordingly.
Okay. We have a couple of more questions, but I think we can leave them to the end of Jerome's presentation. So I would invite Jerome now to present the second half of the presentation.
Okay, thanks.
Thank you, Jerome.
Do you see the slide okay? Well?
Yeah, I can see it fine.
Very good. Okay, thanks, Chris. Thanks, Antje, for introducing like data simulation and providing this first part. So in this second part, we'll go step back again on data simulation approaches. And I will present briefly what are the two main type of data simulation that we use in atmospheric science, in atmospheric composition especially. And then after that, I will go through a range of like cases that are more challenge and I would say research-based and development-based for data simulation. I hope that will give you inspiration if you want to end the error data simulation, and it will give you inspiration for your research or your projects. So in terms of data simulation approach, I would like to step back from what Andrew put and then go a step back with like a very general equation about data simulation. So as Andrew explained, the goal is to produce an analysis starting from a background at an initial time. And the whole game of data simulation is to use the observations combined with the model information to produce this analysis. And from there, we used the mismatch between the observation Y to the models, and the background. And for that, we use what we call the forward operator H. And then we need, which is called an observation space. And you need to have a function here, K or matrix, that transfer the information from observation space to model space. So this K, this is called the gain matrix. And as I said, it handles the transformation from observation space to model space. And then this model space can be the concentrations, as Antje showed. It can also be parameters or even surface fluxes and emissions. So the whole problem, here it looks very simple, but because of the dimensionality of the problem in atmospheric science and atmospheric composition, we need to find ways to solve this. This cannot be solved straightforwardly here because this is too big. So there's two main approaches, which are the variational approach or the ensemble approach, and we will dive into those right now. So the first one is the variational approach, and then Antje nicely introduced this equation before. So you have an observation term, a model term, and an observation term here. So here I'll have complexify the equations because you have the observation operator H here, as Antje showed, and then you have a model term because this is a 4D Barre simulation. This is in 4D, so you need to include a dimension of time. And within the observation term, you need to run a model forward and backward in order to get the information, the mismatch between the observation and the model at the right time. So as Antje explained, for this, you need to run a nonlinear forecast in the first place that you take from here. You run a trajectory where you compute what you call the departure, so the mismatch between the observation and the model, and then you run iteratively a tangent linear model. So we need to run this tangent linear model because we linearize this model around the full trajectory for computational cost. And we go back after that with all this interpolation, we go back and we bring back the information backward to the initial conditions. And we do that several times, like normally it's like around 40 times in order to minimize this equation, okay? And this is called the envelope. So we do this at a given resolution. We start with like a low resolution and we increase the resolution successively, and you run all this machinery 2 or 3 times, and which is called the auto loop. So you increase the resolution, so you start around like I would say several degrees, and you increase the resolution to 1 degree. So in this tangent linear model also, we need to use simplified physics and chemistry for computational reasons. Once all is done, you can have like initial condition to run another high resolution nonlinear forecast. The way to find the minimum of this cost function is to calculate the gradient of this cost function. And here, in this gradient, you have, like as I said, the model term and the observation term. And then you have then the tangent linear model, M, and then its adjoint to go back in time. And calculating this gradient allows you iteratively to find the minimum of this const function and to find the optimal solution. Doing all this gives you a sensitivity from the observation Y to the model states X. So the other alternative to all this is what we call ensemble data simulation. So the idea is that the model state of the atmosphere can be seen as a probability density function. And this can be achieved by running a sample of this distribution, by running an ensemble of perturbed model resolution. So you run an ensemble of nonlinear forecast, and then you run what you call a sequential data simulation. So I will go in detail in this equation, but the way you solve this is to compute the departure, the ensemble of departures, and you cycle on the observations to compute the analysis. This is what it calls sequential data simulation, because you cannot consider all those observations, all those mismatches at once. This is not computationally feasible. The advantage of this is that, and to briefly talk about the B matrix, you can self-update the model error from this at each data simulation window. Those kind of methods can be costly because it requires a large number of some ensemble. You can imagine if you have a low number of ensembles, you have what you call a sampling error, and then your analysis can be quite wrong. And then in detail, the way you solve this ensemble data simulation, so this is your what you call your Kalman gain. And if you take this equation and you take it at a single observation, this simplifies quite nicely to two major terms. So you have the relative weights of your model error to the observation error. And then you have like a term of like simple linear regressions where you try to find the slope between your observation space and your model space. And again, this gives you a sensitivity from your observations to your model space. So, so my second part, I would like to talk, and I will cover that like widely, about emission deviation estimates. So how can we use data simulation technique, whether it is variational techniques or ensemble techniques, to estimate emission parameters that are inputted into the models. So the reason we want to do that is that emissions are one of the major uncertainties in composition modeling, and they cannot be measured directly. Satellite observation measure concentration, but not emissions. And then there's another aspect is that like the compilation of emissions inventories is a quite labor-intensive task. You need to gather a lot of socioeconomic data, also land use data, and then all this takes time, and then you have a lag in those emissions, and then most of the time you use past emission into your current forecast. And we have the perfect example during the COVID crisis. Those emissions were decreased, but if you were running a model at this time without like corrected emissions, you would have like not necessarily like the perfect answer and the perfect reduction of pollution due to the lockdowns. So emissions is not necessarily emission inventory. Some emissions are based on wind, for example, dust and sea salt uplift, also on temperatures or UV light, such as biogenic emissions. Some emissions can be observed indirectly from satellite instruments. For example, you have the fire radiative power from satellite. You can look at land imagery with burnt area, and then you can detect also volcanic plumes. So what we call inverse method or data simulation method can be used to correct emission estimates using observations and model through data simulation techniques. So first of all, I would like to reinforce that like modeling is crucial for data simulation. And then if you don't have a good model, you won't be able to transfer correctly and nicely the information from the observation to the model space, because you use the model information in data assimilation to extend the inference of satellite observation. So there's many processes on emissions. There is like as I mentioned, forest fire, volcanoes, sea salt, dust, and all aerosol emissions. You have also like the anthropogenic emissions on top of this, and you have like a series of processes that allows you that needs to be represented, as Vincent Henry talked about yesterday, that you need to represent correctly to have a correct representation of atmospheric composition. So the problem of inverse models is can we use data assimilation to constrain not only the concentration but also the emission surface fluxes? And basically, you would have a satellite observation. You can compute this mismatch between satellite observation and the background, and then you would use either your adjoint model, as I explained, or your Kalman gate to go back to the emission fluxes. So the model will allow you to take into account larger scale processes or finer scale processes, and also the chemistry and the transport. The problem that we have in operational data assimilation is that our assimilation window is, for example, at ECMWF in the IFS is 12 hours. In some other operational system, it's like between 3 to 6 hours, maximum 12 hours. So in the research mode, you can have like an inversion system that like run over months, and this is fine. But for operation, this is not the case. So, and you can understand this is a problem if your satellite observation is very downwind in the plume from the emissions. If your assimilation window is short, you won't be able to go back to where the emission fluxes were. So if you think about like if you have like a new type of satellite observations, for example, TROPOMI gives you like a better hope for this. Or if you think about the next generation of satellites, those geostationary satellites, they will give you a much more coverage and also enhanced sensitivity with a short assimilation window. This can be possible. But this is not only the case for all species. So you need also to have an idea how to evolve those data assimilation systems, where we combine multiple assimilation windows in order to transfer the information from a window to another backward in time. And this is quite challenging. At ECMWF, we're working hard to design a new system that could do that. So this is the foundation of the work that is being carried right now at ECMWF. So we have set up the 4D system to have the deterministic information and provide increments on the emission inventory, the surface fluxes, using the 4D information. But we also explore the potential of the ensemble information to constrain also surface fluxes and emissions. This is not operational yet, but the idea ultimately is to compare and combine the two methods to make a hybrid system in order to make it synergistic and hopefully fill the goal that we have for emissions. So the emission problem is like it's a with the range of species that we cover at ECMWF, it's a problem across the scales. On the left hand side panel, this is like a diagram that gives you like temporal scales versus spatial scales of the range of like atmospheric major atmospheric species, I would say. And you can see that like this ranges from 1 second to 1 minute to 10,000 kilometers to 100 years. With CO2 being like a very long life, for example, it lives 100 years in atmosphere, where CO is around living in one month, and NO2 or NOx, it's around 1 day to half a day. So you can imagine like then that like in a spatial extent also, this is different scales. And this is like on the left, what you can see with satellite observation for the 3 species I mentioned, okay? And you can see that for CO2, the coverage is much sparser than for CO and NO2. And then you can see also like the extent of the pollutants. For example, with CO, which is a longer lived species, like you have like much diffuse information because like you have much more transport involved, which is not the case for NO2. And then you can compare this with the emissions, and you can see that the emissions, you can see pretty much like, and this is for anthropogenic emissions, you have pretty much the same picture, not exactly, but you can see like it is matching like where you have like most density of population in the world. So it tells you something that like those species, those different chemical components, are not coming from. They co-emitted in a way. So from one type of activity, you have like different species being emitted at the same time from the same sources. So I will start like with like the short-lived problem, short-lived species problem with NO2. You probably you have been told yesterday that like NO2 is short-lived, is emitted like from human emission from especially cars and industry as nitrogen monoxide, NO, and is quickly oxidized in presence of other pollutants, which volatile organic carbons, to produce NO2. And then NO2 is also destructed like, quickly in presence of sunlight to produce ozone. It's also NO2 makes nitric acid and particles. So NO2 in a way is nonlinear and very reactive. And then NO2 levels are strongly dependent on emissions, but also other factors such as weather variability and presence of other pollutants. So because NO2 is very short, we can like show the problem with what is the problem with assimilation and why just assimilating concentration is problematic. Here you have like the increments. So the increment is the difference between the analysis and the background. Is the effect of the assimilation over winter and over summer. And then you can see you have like significant increments over the land areas, over populated area. And then if you compare this analysis, this assimilation with a control run where you don't assimilate anything, okay, you have like you have an effect at analysis time, okay. But if you run a forecast for 12 hours, this effect completely vanishes because the lifetime of NO2 is quite short and you don't constrain the emission. So there's no persistence of the assimilation for this species. So this is, for that reason, this is crucial to be able to constrain the emissions in that assimilation. And then I will talk about now about the other side of the spectrum. CO2, which is like a very long-lived species, and in CO2, many processes are involved, such as vegetation, ocean, fires, and the soil as well. And then you can see in that diagram that the human's emissions is quite like a residual part of all this. This is not like a very strong signal compared to all the surface fluxes that we have. And this is very challenging then in the question of like, how can we estimate human emissions or have like a timely estimate of human emission within all these strong signal, natural signals. And this will require like very accurate satellite observations and most certainly novel data assimilation methodology as well. To give you an example, I mean, this is the fires from our CAMS forecast at high resolution, the 2020 Australian fires. This is for carbon monoxide here. You can clearly see the plume. Those were huge fires, or you probably see in the news, that like circumvented the entire globe. And then you have the equivalent for CO2. So for CO2, you can see the plume because there was a really strong signal, but you can see that this is very blurred with other signals. For example, you can clearly see like the earth breathing here over Amazonia with like I can hear like anyways, you can hear you can see the vegetation pulsating and emitting and absorbing CO2 every day. Okay, so this is just like an example here of like co-emissions and also the challenging part of like CO2. So if we continue on fires and data assimilation, this is an example of like inversion using carbon monoxide with moped CO over like the 2015 Can someone mute the microphone because I can hear?
Yeah, can you all please mute your mics?
This would be like, yeah, thank you. So where was I? Okay, so this is the example of inversion with moped CO over the 2015 US fires that were like raging over Washington state. So this is where the source of the fire were located, and then the prior of emissions were usually underestimated. And then when you perform an inversion with moped CO, you really correct this and you improve the plume and you intensify this plume. You can do the same with PM, correcting organic carbon and black carbon using MODIS AOD, and you see also the response on assimilation. And this tells you that like you have like you have to, as I said, you have to know that like those fire PM and CO are co-emitted in the fires. So you can think about like, can we use one or the other to correct and try to look if data assimilation can do this. So for example, so this is like the increase on the emissions. So using moped CO, you have a factor 3.3 increase on the emissions. So those are the emissions emission factors here. And then you can look at using this is inverted, but like when you do like a assimilation of MODIS using on OCBC using MODIS, you have a factor 3.75 increase. You can think about using a moped CO directly, and you can correlate this using the Kalman gain to correct PM emissions. And obviously you have the same factor 3.3 increase, because in that work a perfect correlation between those type of emissions was assumed. So the correction factors are close, but not exactly the same, because here we made this by doing the full correction. You assume that like you will just correct the activity level of the fires, but probably not what you call the emission factors. The emission factors are what you link between the activity levels and the amount of pollutant that is emitted. And those are quite different, and there's probably an error between those. So it's important to account in additional error doing so. This is the first step that is really challenging, and this is something that is needed for assimilation in general, for estimation of pollutant in general, because you could think then that you could have correction, for example, of NO2 on CO2 on NO2 anthropogenic emission to CO2 anthropogenic emission as well. This was mentioned yesterday, I think, using NO2 for CO2 detection by Andreas Richter. If we continue again with the fires, and here's to illustrate what could be the impact on methodology of atmospheric composition. This is just the difference between using a CAMSCAI methodology effect on temperature versus prognostic aerosol assimilation temperature. And we can see that, like, if we look at the difference between those two temperature fields, like the fires, aerosols, really impact the temperatures. It tells you that this is really important to have like data assimilation and correction and accurate correction and modeling of atmospheric composition for NWP. And to go further on this, you could think about can the information of the composition give you also an information on winds. And then, so those are the model equation here. You have like the tangent linear equation here, and then the adjoint equation, the model that goes backward. And by including the tracer information, the tracer evolution in the adjoint equation will give you an information on wind. So this has been tested, and this is like has been proven that you can have an effect on the wind values using, for example, an ozone increment in the stratosphere. So if you look at the initial time, so 9Z is the initial time, the increment, there's no increment on the wind because you don't give the opportunity to a joint to act on the wind because there's no back and forth in time. So this is similar to what we call 3D VAR. Okay, this is just three-dimensional. There's no other dimension in time because in 3D VAR, you assume that everything is at initial time, and you don't run a tangent linear adjoint. But then if you go forward in time and you look at the increments with an observation at 12Z or 15Z, you can find an increment because you give the opportunity of the tangent linear and adjoint to act from composition to the winds. In the same vein, but this is more using the ensemble information, there were tests done using CO2 and methane satellite information to constrain NWP. And then it was found that you could have like a slightly positive impact on relative humidity in the stratosphere using CO2 and methane information. And this is quite important actually to potentially explore this because in the stratosphere you have not as much information for NWP than in the troposphere. So maybe atmospheric composition assimilation could play a role here. But at the same time, and this is would be one of my last slides, that data assimilation, for example, in a stratosphere of atmospheric composition can disrupt NWP. This was an example that we had during the ERA interim productions, is that we had ozone increments in a stratosphere, and those increments, because of the coupling between the chemistry and the methodology, was not done properly. The 4D VAR was just trying to react to this and create huge temperature increments and wrong temperature increments in upper stratosphere. So yeah, the 4D VAR tries to adjust the flow where it is less constrained and trying to improve. The 4D VAR was doing this in order to improve the fit to observations. So now the IFS ozone analysis is completely uncoupled to the methodology now. So just to finish, I think in summary, so I think it's important to keep in mind that different data simulation approaches exist to solve the same problem, to combine satellite observation with model, to provide best estimates and forecasts. So one current operational change that we have in atmospheric composition is the estimation of surface fluxes and emission using data simulation. So one thing that is for sure, the operational system needs to evolve, and this will be greatly helped by the new generation of satellites. So we saw that atmospheric composition is ranging over multiple order of magnitudes in scales. This poses a challenge, but also a great opportunity. I think atmospheric composition data simulation could be an added value for numerical weather prediction, but to the risk of degradation of NWP, if not done properly, because NWP, I think, ranges in errors that are much smaller than the atmospheric composition. And I think this is the time to stop. Thank you.
Hey, thank you very much, Jerome and Antje. That was an extremely good introduction to data simulation, very interesting. So we have a 5 minutes coffee break, then we reconvene. So we have a couple of questions on the Slido, but I think it's probably a good idea not to answer them now because we only have running a little bit late, but we can answer them properly during the question and answer session after the satellite applications session. So we can have a very short break of 5 minutes, then we come back at 11:05 for the second part of the satellite application session. So thank you. Thanks again, Jerome and Antje.
Yeah, sure. Okay.
Okay, so welcome back. I'm sorry that that was such a short break. Maybe in future we'll have a slightly longer coffee break to allow for a bit of margin. But now we're going to start the next. So the second part of the satellite application session. The first part was yesterday, and I have great pleasure in introducing Cathy Clerbaux from the Laboratoire Atmosphère Milieu Observation Spatiale, LATMOS, and also the Institute Pierre-Simon Laplace, EPSL. So Cathy is going to present carbon monoxide from the IASI satellite, a good tracer for fire plumes and for local pollution. Cathy, the floor is yours.
Thank you, Chris. Do you hear me well?
Yep, we can hear you loud and clear.
Okay, good. So I'm going to tell you, I'm going to give you some inputs on what we see from space. You have already seen several nice illustrations of what satellite can provide to track atmospheric pollutants. And here I will focus on carbon monoxide. I'll say a few words on other pollutants at the end of my talk, but it's mainly focused on carbon monoxide. So I'm a senior scientist. I work at LATMOS. I have a whole crew working with me. So most of the plots that you will see have been provided by PhD students or postdocs working with me, because satellite data can be very overwhelming. We have a lot of data. I'm trying to, okay. We have a lot of data, and my main work is work on the ESA mission. So here I have a movie that presents, in fact, what the ESA mission is. This is ESA. It's like a cubical device that measures 1 meter cube, and it's sounding the atmosphere using the thermal infrared emission of the Earth. So it records, in fact, every spectroscopic signature of molecules that are present in the atmosphere. And this is an old movie, so there are 2 ESAs on that movie, but now we have 3. We have the first one was launched in 2006, the second one in 2012, and now we have a third one that was launched 2 years ago. So as I said, it uses the spectroscopy properties of molecules that, in fact, each of them have spectral characteristics that provide what we call spectra. And if you analyze each of these data, so each little red dot that you will see here provides an observation like the one you see here. This is a spectra. And from that spectra, we can really identify spectral signature of a bunch of molecules that appear in colors. And we analyze these measurements, and if we know the temperature correctly, then we can make a guess of the atmospheric concentration. Okay, so this is one typical spectra, and here I'll focus on carbon monoxide. And this is a very interesting molecule because it's a very good tracer of any activity that includes burning. So it means we can track fires with CO, we can track like everything that is producing CO is related to combustion. So industry, traffic, fire activities, domestic heating, everything we produce CO. It has a quite long lifetime, between 1 and 3 months, depending on the season, because it's destroyed by reaction with OH. And it accumulates in the atmosphere. So usually when you look from the satellite, you have a view of a CO map, and then you have a hard time to discriminate what comes from what, because everything is accumulated. I'll show you an example. So by the way, we have a lot of other molecules that we can track with ESA. They are provided here. We have a list of more than 30 molecules. And of course, not all the time we see all of them. It depends on, for example, if we look about fires, we see several of them. If we look about above a place where there is a lot of pollution, then we see other molecules and so on. So, but let's start with CO, carbon monoxide, and let's have a look at what we see with long distance transport. So this is a quick reminder. Transport in the atmosphere is, of course, driven by the presence of wind, and it depends on where you are located. But basically, as a rule of thumb, it takes a couple of weeks to go from one continent to another continent, 3 or 4 weeks to make the circle of the Earth. And if you want to go from one hemisphere to another hemisphere, then it takes more than a year. It means that for carbon monoxide, I told you the lifetime is about 1 to 3 months. It's basically, it can spread all around one hemisphere. So if sources are located in the northern hemisphere, then the CO will stay in the northern hemisphere. On the contrary, if you have some sources, for example, here over Australia, we'll see that in a minute, then it will stay over Australia. It can travel basically at the same latitude. Okay, this is an example. This is an animation. How to do this animation? We take the daily maps of ESA and we do a smooth average over a few days so that we can get rid of all the missing data. Missing data with the ESA satellite would be observation, for example, that are contaminated with clouds. If there's a cloud on the way, then we don't see what is under the cloud. So basically let's have a look at these maps and describe what we see. So we are in January, and what we see is high contents of CO everywhere in the Northern Hemisphere. It can travel with the winds. There are high levels also at some location, like have a look here in China, India. Then it's decreasing. Now we are in the summer. It's decreasing because the chemistry is more active. There is more sun, there is more OH, so the chemistry is more active, and the level of CO is lower. Have a look here over Africa and Southern America. This is the time of the year where you have very large fire over these areas. And as you can see, it is also somewhat transported. You see that with this animation. Let's have a closer look to some of these events. So a very striking event is, so on the top plot here, it's the same, it's a smoothing average, and it's 2014. That would be a very typical year. So during autumn, after the summer, what we see is very large fires in Central Africa, America, and also in Indonesia. And if you compare a year with one other year, like let's have a look at 2015, there was an El Nino episode going, and it means more dryness at some location, like for example in Indonesia. And so we had a record spread of carbon monoxide due to the fires occurring in Indonesia, and then the CO is spreading with the winds well around both west and east from Indonesia, and spreading even near Africa, as you can see. Let's have a look at a more recent event, Australian fire. So Inness, and also I think Jerome mentioned it. In fact, these huge fires that occurred, and that we can also track with EASI. So by the way, EASI is assimilated in the CAMP system, and that's why we have very similar type of animation. So large fires in the south east of Australia, as you probably all remember, mostly around the Sydney area. Here on this picture, it's a visible picture taken from the MODIS instrument. What you see is really the plume, the ash plume that is spreading and leaving from going east from Australia. If you look now at the EASI data on this animation, so Australia is now here. What you see on this animation, it is the same plume, and it's really moving, and it's reaching, in fact, the coast, the west coast of South America, and it's traveling across again here to reach the coast of Africa. And then if you have a look, so this is the Earth seen from the bottom, I would say Antarctica, Australia is here. If you have a look at the average over a few days in January, what you see is really the CO plume is like traveling all around the globe and coming back. You see that here, and then it's moving again, and then you see here the plume is coming back from where it started, in fact. And with the EASI mission, it's the very first time that we saw that from space. In fact, the whole plume traveling around and coming back to where it was emitted. So most recently, the fire over California. These are very impressive pictures. And here again, a nice animation where you see the fire, and then you see it's the plume, the CO plume is really crossing the ocean and reaching the coast of Europe. It's basically the same type of animation that you have seen in the previous talk, but here it's only with the satellite. So it's great that we can see that directly from space. We can really track the CO patterns, how it's crossing the ocean, and it lasted for several weeks, in fact. So very intense plume, it's huge. In terms of carbon monoxide, it's a huge episode. Okay, so now that we have seen how far carbon monoxide can travel, and I've also mentioned that it's generated, the carbon monoxide is generated by several sources: industry, heated systems, road traffic, and also okay, this is because I need to talk about other pollutants. Agriculture practices also will emit pollutants. And you have here the main pollutants that are involved in each emission sources. So we thought also with the team that are looking at this data every day, we thought, okay, what's going on during the lockdown that are occurring in different countries? What can we see with CO and other pollutants? And in fact, we have worked on that for several different countries. So if you want to have a look at what we did, it's all summarized in this website. I'm giving the address here. I think if you just type IASI and COVID-19, you directly found the page. And I'll show you two examples, one over China and one over Paris, in fact, in France. Okay, so you have seen that in the past. I think the very first satellite mission that showed some impact of this lockdown was on NO2, and it was Tropomi on Sentinel-5P, and you have seen this plot before, I'm sure, where you really see a drop of NO2 over cities. So remember, for CO, it's quite different because NO2 has a lifetime of a few days, whereas CO has a lifetime of weeks, even months. And so let's have a look at what we see over China. It's quite tricky, in fact, to look at that because it's not the same amount of CO that is emitted or that is not emitted because of the lockdown that what we just saw with the fires. It's way less, in fact. So we have to track that. And China is a good place to start because first the lockdown started there. And also because the level of CO is so high usually that if you see a drop, probably it's over that place that the drop will be the most significant. So remember the second or third slide that I show you, the CO level are changing very much with the season. There are higher level of CO in the winter, lower level of CO in the summer. So we are here in the winter, so we need to compare apples with apples. It means that if we want to track a drop on CO, we have to look at the previous years, same time, exactly the same time. Otherwise, there's no way we can compare. So this is the start of the lockdown in China in 2020. You see quite high level of CO here. And then if you compare to the previous years, in fact, this is an average with ESA of the 2 previous years. You see that we have an increase of CO when the lockdown started. And this is basically due to fires that occur at that time, large fires that were occurring in Malaysia, and the plumes were transported in the south of China. This is just before the lockdown. This is in fact during the lockdown. If you compare, so the bottom plot is what we observed this year, and we compare with the top plot, the average of the 2 previous years. As you can see, during the lockdown, we definitely see between Wuhan and Beijing, we really see a drop of the CO concentration. And this is linked with the fact that there were less road traffic, almost none, less industry, several industries had stopped working, and probably the domestic heating was still there because people would stay at home. But the combination of the three, in fact, turned out to be a lower level of CO that we could really easily see with ESA. If you compare now with after the end of the lockdown, so the CO came back directly when activity resumed, in fact. So this was my first example. So it's pretty easy to see over China. It's less easy to see over some other areas of the globe, like, for example, over Paris, we have, oh, okay, that was my difference plot. Sorry, I forgot that one. Different plot showed we have like seen between 30 and 40% of decrease between Wuhan and Beijing during the time of the lockdown, in fact. Okay, coming back to Paris. In Paris, the level of CO are low because there's not much use of coal. There's not many sources of carbon monoxide. When we have pollution event in Paris, it's particular, like for most of the place, but in Paris, it can be very heavy. In particular, over March and April, we have usually several days per year that we have pollution alerts because the air is full with particles. So we thought, okay, maybe let's have a look of what's going on during the lockdown. And the lockdown in Paris started at the end of March, in fact. So these were the local observation. In fact, this is not satellite data. Those are local observation of NOx and also particles. And what you can see, and the lockdown is indicated by this black line here. And what you can see is as soon as the lockdown started, few days after, the level of NOx really dropped. So no car traffic means the level of NOx is really low. But as you can see, the level of particles, it's low, but there are some large peaks. Like for example, at the end of March, there was a very large peak here. So it was a very good experience for us, because usually you have a mixture of sources that are combined together, explain the level of particles that we see. So usually the car traffic is involved, the heating systems, like any chimneys that is burning firewoods, for example, would also release particles. And of course, also one big source is agriculture. Where is it coming from? So agriculture, usually when you use fertilizer, you spread ammonia over your field, and then when it's evaporates in the air, it degrades into particles. And so here this time, during the lockdown, we had an opportunity because there was basically no car traffic as shown here with this plot. But when we measure ammonia, this is local measurements of ammonia. These measurements were taken over the roof of our university. You can really see an excellent correlation between ammonia and the level of particle. It means that for this year, in fact, most of the particles were directly linked with ammonia. And what do we see with satellite? We can measure ammonia with IASI. It's also obvious from the satellite maps that there was a large efficient spreading of ammonia because the weather was excellent. The conditions were perfect to spread ammonia. In fact, these very high levels of particles that we saw in Paris, even during the lockdown, were associated with the spreading of fertilizer during this weekend here. It's obvious from the plots. Okay, that ends with what I was going to tell you. So several of examples of what we can see in terms of pollutants, how far they are transported, what we can see for local pollutants also. There are several other molecules and products that are available from the IASI mission if you want to use them. Is the website. There are also some plots. I think some of you probably already plotted some data. In particular, CO is one of them easier, in fact, to access because we have a full data range for this one. And there are other ones that you can see here. Thank you all for listening.
So thank you very much, Kathy. That was a very interesting presentation on carbon monoxide monitoring. I think we have time for one or two questions. So on the Slido, there was one question on CO in Wuhan. So during the lockdown in Wuhan itself, there's no CO reduction, but only north of Wuhan. So during the lockdown in Wuhan, there was only CO reduction north of Wuhan. Do you have an explanation for that?
Okay, that's a good question. I would say not really. I think part of the fires that occurred a few weeks before that I showed on the left plots were still there. So on the southern part of Wuhan, there is some CO left from the fires. I think that's most of the answer, yes.
Yeah, and what is the yearly variation? That was the second part of the question.
The yearly variation for CO? It's a lot. So it accumulates during the winter. So the peak of CO, like in all the northern hemisphere, would happen in March or April because it's all accumulated in the winter. And then the suns come back and then the chemistry starts to be more active. So it's like really dropping. And the lifetime of CO is also diminishing quickly. But you have to think, you have to discriminate local sources, they accumulate with CO because the lifetime is long enough so that it travels. So usually from the satellite data, we cannot discriminate what comes from fires or what comes from traffic roads, for example.
Okay, thank you, Kathy. So I think that was very much appreciated. We'll now go on to the next presentation, and I have great pleasure in introducing Anna-Maja Sundstroem from the Finnish Meteorological Institute and the EUMETSAT Atmospheric Composition Monitoring SAF. And Anna-Maja will present satellite applications on aerosols from local sources to long-range transport. And if I could just remind everyone to please mute your mics. Okay, all of the participants of the training, if you can please mute your mic, that'd be great. Okay, so thank you, Anna-Maja. The floor is yours.
Thank you. So good afternoon from Finland to everybody. I'm Anna-Maja Sundstroem and working at the Finnish Meteorological Institute. And also the FMI is leading the EUMETSAT Atmospheric Composition Monitoring SAF, so I am also part of that team. And today I'm going to talk to you about satellite applications on aerosols. And I hope that you are not too tired, so this has been quite packed before noon, so I hope you hold with me on this. So the contents of the lecture will be a short introduction overall to the aerosols. Then I will just go through satellite observations of aerosols overall. So I will introduce AOD, absorbing aerosol index, and absorbing aerosol height. So I think this whole week so far has been actually a really good intro for my lecture today. So aerosols have been mentioned each day and from many different aspects. So I hope that my presentation will now wrap up then this, what you have already hearing about aerosols. And then as a last point, so I will show you an example case of the US fires from this September. So first of all, I want to play you an animation that is based on a model. So here you can see different aerosol types and how they are transported from their local sources around the globe. And each of these different colors in this animation denote a different type of aerosol. So you have dust, organic, and black carbon, sulfates, and sea salts. And you can see quite nicely the aerosol, how they are emitted from the source regions and how they are then transported with the meteorological systems. So for those who are not familiar with aerosols, so this is something really basic. So with aerosols, we mean solid or liquid particles that are in the Earth's atmosphere. And the aerosol sizes really can vary from nanometers to hundreds of micrometers. And there are basically two types of aerosols. And it was really nice that Kathy just showed you the ammonia example and how the relation goes with the PM, so the particulate matter and aerosols. So we have two types of aerosols. First, when we are talking about this kind of primary aerosols or primary particles, so those are those kind of aerosols that are emitted directly into the atmosphere. So from the cars, from the pipes, industrial complexes, so that are the primary aerosols. But then we have this other type of aerosols that Kathy just actually showed. So they are actually not emitted directly into the atmosphere, but they are formed in the atmosphere via gas to particle conversion. So we are calling this kind of nucleation. And so you have gases in the atmosphere, and then with the presence of a UV sunlight, so there is this kind of conversion from gas to particles happening. And this is also partly the reason why, for example, the air quality problems related to aerosols are really tricky. So you can apply different kind of filters to this directly emitted primary aerosols and control those emissions. But this gas to particle conversion is then a much more trickier part. And as from the animation, you also saw that the sources for the aerosols can be both anthropogenic and natural. So there are a lot of natural emissions from the dust, for dust and sea salt, for example, and then of course anthropogenic emissions from the different kind of industrial activities, for example. And for aerosols, so the residence time in the atmosphere is typically varies from few days to weeks, and this is very highly dictated by the meteorological conditions, for example, and also at the heights of which the aerosols are released in the atmosphere. So as I said, this week has been already, there has been discussion about the aerosol observation systems, and at the beginning of the week, I think it was a Monday, so you were covering these ground-based measurements of the aerosols also, and today's talk, then I will cover the satellite part of the aerosols. And this is just giving you an overview that both from satellites and from ground-based observations, we have this passive type and active type observations. Today, I'm only concentrating on this passive aerosol observations. And so basically, there are different kind of spectroradiometers that are using they are basically observing the solar light. And what you can get from these kind of passive satellite instruments are the optical depth and absorbing aerosol index, for example, plus many other parameters depending on the retrieval algorithm and the instrument. And these kind of other parameters could be, for example, the layer height or fine mode fraction or this kind of other parameters. But the aerosol optical depth, I believe, is the most commonly known satellite-based aerosol parameter. So now when we're talking about aerosols, so the aerosols can scatter and absorb solar radiation. And this is now a little bit different type of approach dealing with the aerosols in the optical remote sensing than dealing with the gases, because aerosols do not have this kind of specific, very sharp absorption peaks at a very defined wavelength ranges. So we are dealing with the scattering and absorption at the same time. And the key aerosol properties that define how the aerosols actually interact with the radiation are, first of all, how much there are aerosols, so the aerosol loading, and we call it optical thickness, so how much aerosols there are. Then another important thing is the aerosol size distribution, or the aerosol size, and especially its relation to the observed wavelength. And then this is also has to do something with the aerosol shape. So size distribution and shape affect to the interaction with the radiation. And then we have aerosol chemical composition. We are often talking about aerosol types. So the refractive index and the complex refractive index of aerosols are dictating how much the aerosols absorb the radiation. And there we have also very important term, single scattering albedo, that is usually referring to the specific aerosol types, and that tells you what is the relation between the scattering and absorption. So how much what is the ratio between absorption and scattering of this specific aerosol type? In the optical sense, if we think about aerosols, we have very limited number of general aerosol categories. So in the previous animation, you already saw those aerosol types. So in an optical sense, we have only this kind of limited number. We have dust type, we have sea salt, we have biomass burning. And so in aerosol typing, in this sense, we can only separate only a number of different types that have optically different properties. So first, couple of words about aerosol optical depth, which I think is you are all quite familiar with this parameter, but I think it's still good to go through what it is actually about. So most of the time, I think we are using AOD or AOT, so optical thickness, it's the same thing, two names for a same parameter. And so AOD is related to the amount of optically active aerosols in the total atmospheric column. And as already previous slide showed, so it can be retrieved from satellite and ground-based instruments for cloud-free cases. So this AOD parameter is really sensitive to clouds, and therefore this kind of cloud screening in the process of aerosol retrieval is very important step. And so we can derive the AOD from using this extinction coefficient. So it is basically the sum of, it tells you how much the radiation is attenuated by the aerosols, and it is the sum of absorption and scattering parts. So we are using this extinction coefficient. And by the definition, AOD is basically the extinction coefficient integrated from the surface, from the Earth's surface to the top of the atmosphere. And so there we have AOD, and since the units of the extinction coefficients are inverse length, so then when we integrate it over the atmospheric column, so AOD is this kind of unitless parameter. And I told you that the AOD is related to the optically active aerosols. So in these figures, I now want to, in a simple way, illustrate what I mean about this optically active aerosol. So here in the left, so you can see this is a real measured aerosol size distribution, so measured from an in situ device. And then in the right side, so I have done a very simple modeling of using this real measured aerosol size distribution. And I have now modeled the contribution of each aerosol size to the total extinction. So basically, this is you can think of this as a contribution of particle size to the AOD. And this is now done at the 550 nanometers wavelengths. So what I want to say in this image is that if you think of this 0.1, so when the particle diameter is below 0.1 micrometers, so you can see that there are, in the number concentration, there are quite a lot of particles. Here, actually, the largest single number concentrations are obtained here. But if we look at now what is the contribution of these size particles to the AOD, is very insignificant. So actually the AOD this is now the optical part, so the optically active aerosols. So there is this kind of difference that what particles actually the satellites are able to see, and satellites cannot see the smallest aerosol particles. So there is only a part of the whole aerosol population that can be observed with satellites. AOD retrieval, I'm just showing a very, very simplified and basic principle of how it is done. And so I'm not going into the details here. But the AOD retrieval is basically based on cutting this measured top of the atmosphere reflectance into different kind of pieces and then pulling out the aerosol contribution from the measured signal. And so these are kind of the basic steps are done during the retrieval process are done. This cloud screening, which is in very important step in order to get a correct AOD out. Then we need to do a Rayleigh correction and then surface correction, and then you can get the aerosol contribution finally out. But this is, as I said, this is very oversimplified version of the retrieval process, and there are many, many, many fancy mathematical methods how you can actually do this retrieval. Here I illustrate this same problem. So here is an image taken from this article here, and they have basically modeled the top of the atmosphere reflectance, so this part here, as a function of AOD. And one of the complex problems is that AOD over aerosols over different types of surfaces can have very different type of effects on the TOF reflectance, and therefore this surface correction is a really tricky part of the retrieval process. So here, if you look at the lower line, it represents so-called this dark surface. So when there are no aerosols, so the TOA reflectance is also rather low, and the upper line here is a so-called bright surface. And now I have here the boxes for bright surface and dark surface, and this is now without any aerosols. But then when we put the aerosol on top of this surface, so if you look this situation now from space, so what can happen, for example, this one type of aerosols is that when they are overlaid over a brighter surface, so you might get a little reduction on this top of the atmosphere reflectance. But when you put the scattering aerosols on top of a very dark surface, so you can actually get quite an increase in the top of the atmosphere reflectance. And this is the kind of the basic problem that we need to be able to solve in the AOD retrieval process. And of course, this can be the other way around when you have a darker aerosols and bright surface and all these kind of different variations. And that's why this is such a tricky problem. AOD is very highly wavelength dependent, and most typically the AOD is given at 550 nanometers. What AOD doesn't tell you is about the vertical distribution of aerosols. However, we can also quite often say and quite confidently say that, for example, over urban areas, so the aerosols are located within a few lowest few kilometers. But here in this image, I have illustrated two different cases where there is basically urban aerosols in the lowest levels, atmospheric levels, and the AOD is 0.3. But the same AOD at the same wavelength can also correspond to a case that you have some kind of aerosols at the lower levels of atmosphere, and then you have some elevated layer here. So this is the information that you will not get out from the AOD. Satellite AOD is available from several instruments and wavelengths with many additional parameters. Here I have listed some instruments, and I think there are many more, so this list is not complete, but just to give you some kind of idea about the instrument names. And later on, so I will then show also one example related to this PMAP aerosol AOD. Here is a global image now, 1 year mean of AOD from the MODIS Terra instrument, 2019 mean. And this AOD, for those who are not working with the aerosols, so AOD is always a little bit tricky parameter to be described, because it doesn't basically tell you, most of the people, almost anything. So if you say that AOD is 0.5, so if you are not familiar with the AOD aerosol retrieval, so that might not tell you too much. So therefore I took this image and wanted to show you what kind of a yearly AOD mean at 550 nanometers look like. And so if we calculate the global mean, so it's about 0.15. And so that is the kind of the mean AOD for the whole globe. And typical range for this at AOD at this wavelength, the variation range is 0.05 up to 2, and 2 would be already a really polluted case. And one very nice thing about AOD is that it has been actually observed from several instruments for many, many years. And there are actually time series and harmonized time series for over 20 years already of this AOD, which is really long observation and nice time series to look at also this kind of long-term variations of the aerosols. And here actually you can also see some kind of characterizations of which each of these aerosol high AODs are here in Asia related to anthropogenic pollutions, and then there are some biomass burning areas, dust areas, and biomass burning also is quite a significant factor also here in the north, considering the AOD. I also wanted to say a couple of words about the one hot topic that has been studied for several years now, and that is the satellite AOD versus this particulate matter, so PMs, as we talk about. And there are, during the recent years, there has been many studies studying this this relationship. So as you know, all the national and international and national air quality standards considering the particulate pollution are based on this amount of particulate matter, so the in situ measurements, and we are talking about PM10 and PM2.5. And since both AOD and PMs are related to aerosol concentration, so there is of course quite often some rather good correlation between these two parameters. And as I already said, so satellite-based AOD has been used in many applications to estimate, for example, the global PM2.5 concentrations. And here are some references if you want to look at the very early works on this. But there are a few remarks that I would like to do and say, maybe if people are not very familiar with the aerosol observations overall, so this is maybe a good to remember. So there are still some significant differences that needs to be taken into account when you start to make these kind of comparisons between AOD and PMs. So first of all, as now said, so AOD is a total column, and also there are always possibility that there are elevated layers of aerosols, whereas the PMs are from the surface concentration only. With AOD, so we cannot, in an optical sense and in optical measurement, we can't distinguish the aerosols exactly by their physical size. So we cannot say when we do optical measurements, like now we cut out all the aerosols that are above certain diameter, for example. And this is the difference also for this PM measurements. And one also a really affecting feature is that AOD is always given at ambient relative humidity. So it's at that relative humidity where the aerosols are at the moment. And some for this kind of hygroscopic type of aerosols, so the aerosols are actually swelling when there is more humid air. And that affects also then to the total AOD, of course. But these PMs are always defined from dry particles. So this is also one thing that needs to be taken into account when you make such comparisons. But overall, there are many very interesting studies considering this topic. Okay, maybe a little bit less known parameter for the wider audience from the satellite instruments is this absorbing aerosol index, or AAI. So this has been also mentioned in some of the presentations previously this week, but now I will go through this parameter. So this differs from the AOD from many perspectives. And sometimes you also call this aerosol index. This has also many names, and sometimes you also know this as a UV aerosol index, and the UV comes from the fact that this absorbing aerosol index is defined using UV wavelength. So you need a UV type of instrument where you can define this aerosol index. Typically the wavelength range is about 340, 388 nanometers. And here are listed a couple of these instruments where you can obtain this aerosol index. So GOM2, TROPOMI, OMI, and OMPS. And as this absorbing aerosol index also already states, so this index is sensitive to absorbing aerosols. That means smoke, volcanic ash, and desert dust. So these are the three types of aerosols that the aerosol index is sensitive to. And that means that these type of aerosols have a significant absorption in these UV wavelengths. And basically the aerosol index, as the name also said, it's an index, and it has a much more simpler retrieval algorithm than the AOD. And so basically the AAI is separating the spectral contrast at two UV wavelengths that is caused by aerosol extinction, and then it separates that effect from the other effects, for example, from molecular scattering. So this is, in a way, this is a much more simpler retrieval approach than what is for AOD. And the good thing for this aerosol index is that this is not as sensitive for clouds as the AOD is. So we can also obtain this from cloudy scenes when the aerosols are on top of the cloud. So of course, below clouds, we cannot see. And that is why the AAI is a really good tracer for smoke and dust and ash plumes. There are a couple of things that are really important to remember when you interpret this AAI. So here I have an example image from GOM2B one day, 1st of June 2019, and here are plotted all the AAI values. So you can see, first of all, that the AAI ranges from minus values to some positive values. And now these positive values are actually indicating where our absorbing aerosols are. For clouds, the index is close to 0 or slightly negative. And so what we are really interested when we are looking at the aerosol index, and if we are interested about aerosols, so what we are interested in is only these positive values. And for this kind of plumes, so we have typically the aerosol index is above 1. And as you can see here, the background is slightly positive, but the plumes have typically, like here is the one plume from Canadian fires, so it has really highly positive values. There is also one special feature, which is the sun glint that creates over the ocean this kind of positive from south to north type of features to the maps. These are typically taken care of if you apply the quality filters, the quality flagging to the satellite data. So these are taken care of, but just be aware that if in your maps there appears over the ocean this kind of north to south stripes of very highly positive values, so check that they are not sun glint and they are really related to the aerosols. And as said, so the AAI is available from multiple instruments. So we have GOM2 and ACSAF is providing the aerosol index from this GOM2, A, B, and C instruments. We have TROPOMI, OMI, OMPS, and then we also have a very nice time series of AAI, which actually extend over 40 years. It's a really long time series. So there is the multi-instrument AAI is a composition of several different instruments, and this is also a really long time series. As I said, so that the interpreting AAI is not always very straightforward. It comes from the fact that the AAI is not only dependent, for example, on the aerosol loading, but also many other factors. And so this is also a caution to you if you are using the AAI in your project works. So comparing very different cases with each other is not necessarily straightforward. So this is also good to remember. So AAI, even though it's related to the aerosol loading, so the amount of aerosols in the atmosphere, it is not as direct measure of it as the AOD is. And with AAI, you typically see an elevated plume. So if you want to make some kind of assessment, for example, about air quality based on AAI, so I really highly recommend to use also some other sources of information than only the aerosol index. And here is this image. I hope clarifies you a little bit more what's this about. So we have optical depth here, and we have aerosol index here, and then we have these different lines represent aerosols at different heights in the atmosphere. And so now if you look at the optical depth, we take 1, and then we look if the aerosols are lower in the atmosphere at 1.5 kilometers, so the aerosol index can get a value about of 2. But if the aerosols are higher up at 6 kilometers, so the aerosol index can be even 6. So increase in the aerosol, you don't need an increase in the aerosol loading, but the index value can go higher up just by elevating the aerosols to a higher atmospheric level. So this is a really good thing to remember when you are working with the AAI. And here I have now one example of AOD versus AAI. So what kind of different kind of interpretations you can make with these two parameters. This is an example day from 1 year ago where there was a huge pollution case. So that this is the AOD in the upper figure. So here is Beijing is somewhere here, Delhi is somewhere here, I think. And so there were a lot of aerosols in both countries, and the aerosol was varying from 0.5 to up to 2. So there was really a severe pollution cases in both countries. But at the same day, so the aerosol index was only elevated over India, and we didn't see any indications of aerosol index over Beijing, for example. And so why the difference? So that is the aerosol type. So what we can conclude based on this kind of comparison is that we have absorbing type of aerosols, and a lot of them over the India, whereas most probably then over Beijing and over China. So the aerosol type has been more scattering, and then therefore the AAI doesn't show anything. So this is the kind of analysis that you can make when you compare these two parameters. And then finally, just very quickly, this is a new product provided by the ACSAF, also from GOM2. So this is the absorbing aerosol height, and it's based on also the aerosol index retrieval from GOM2. And in addition to that, it also uses the information from this Fresco cloud algorithm. So basically what it gives you is the aerosol estimated absorbing aerosol height in kilometers for those significant plumes that you can see with the AAI. And there is also some words about the usage of the aerosol height. So this should be analyzed with AAI, and the aerosol height can be retrieved only for those cases where we have enough absorbing aerosols in the air, so that you can make a reliable retrieval of the height retrieval. So this is a new product, and this can be also obtained nowadays via the ACSAF distribution system. And this aerosol layer height that is related to the aerosol index is also nowadays available from Tropomi. So from both instruments you can get, when the plume is significant, so you can get this estimation also about where at the height of the aerosol plume. Okay, my last couple of slides are about the fires in the US September. So I will show you 3 parameters. So the PMAP AOD, GOM2 absorbing aerosol index, and then the aerosol height. So in this September, so there has been a lot of fires in the US, and during actually the whole month, there were some very significant transport events also where the smoke extended up to Europe. So in early September, still the fires were more located to the western coast, and so the smoke was also moderate, even though it created very bad and severe air quality problems already in those locations where the fires were detected. But then during the month, when the weeks went by, so there started to be more and more smoke emissions also from these fires, and with favorable meteorological conditions, so the smoke was also transported towards Europe. And here is now, from the same day, so here is now an image of the PMAP AOD over the US, GOM2 aerosol index, and then the aerosol absorption aerosol height. So as there were more fires and more favorable meteorological conditions, so the smoke spread really over a really huge area. And here you can see the aerosol index, even though there was cloud. So this is kind of the nice thing with the aerosol index, that it can kind of tell you how wide the plume is. And here is the corresponding absorbing aerosol heights. So as you can see here near the source region, so the aerosol height was rather low, whereas over this transport area here, so the absorbing height was actually much higher, about 8 kilometers or so. And then here is the PMAP AOD that tells you actually about the aerosol loading, and this is very typical AOD figure. So as I said, there was many clouds. So typically then the AOD for a 1 day looks like this. But this still, anyhow, this gives you a lot of information about where the possible air quality problems are and what kind of total distribution of the total loading of the aerosols are in which location. And I think this line here, where the smoke, there is this kind of a clear difference between the loading is somewhere located somewhere here. So we can see that the AOD was as high as 1.2, and this is really an extreme loading for US conditions. And finally, also how the situation evolved considering the smoke transport later in the month. So there were, starting from the 14th of September, so the smoke was transported all the way to the Europe several times. And so, take-home messages. Satellites offer a very efficient way to monitor aerosols on a global and local scales. And these 3 parameters can be used in many applications. But at the same time, it is really important to remember that the interpretation of each of these parameters is important to remember, so that you will know what these parameters tell you and what they do not tell you about. And for air quality assessments in general, I recommend that you would combine this satellite-based information from from several other sources, for example, with other satellite data or then model data. So thank you.
Thank you very much, Anna-Maria. That was a very good introduction to aerosols and how to monitor them using using satellite data. So that was a very good, very interesting presentation. What I would now propose to do is to end the streaming on YouTube, and then we would have a discussion session